Ready?
Very good.
Let me check. All right, shall we? Did everybody get their food? Did you have thin crust pizza today?
Thin.
Huh? Thin?
Yes.
My favorite. All right, so here's another Kent seminar today. Our presenter today is Rebecca Yang, one of your colleagues. And she's really going to talk about a really cool sustainability tool. And that came out of our Illinois tollway study. And she'll probably talk about that tool a little bit, but her presentation will be about use of that tool to evaluate some of the sustainability strategies for pavement construction, which may include asphalt and concrete pavement applications. A little bit background about Rebecca. I know you all know her very well, but she is currently a PhD student in our department. I don't need to do this, of course. I know her very well. And then she finished her master's degree, 2014, right? And she's been working toward her PhD on pavement sustainability with Dr. Al-Qari. Let's just give her a round warm of applause and get her presentation started.
Okay, Josh, is that good? Or just want to make sure. Good. Testing 1, 2, 3.
Yeah.
Okay, great. All right. Yeah, thank you, Dr. Ozer, for the introduction. And as you mentioned, I'll be talking today about the use of the life cycle assessment tool to evaluate sustainable strategies for pavement construction. And before I go on too much, I wanted to also acknowledge the two co-authors, Dr. Al-Qari and Dr. Ozer, who have been also a part of this work. So an outline of the presentation. So we'll start with an introduction to sustainability in general, kind of the motivation behind the overall project. And then we'll move on to the life cycle assessment study that this tool is a part of. So we'll give a brief overview of that. It's a pretty big project that's been going on for a couple years. Next, I'll get into the development of the tool itself. And then we'll move on to the two different analyses that were done using the tool. And I'll end with some final remarks. So the introduction, as many of you know, sustainability can be defined in a lot of different ways over the years. One of the more popular definitions is from a British businessman, John Elkington, from 1994. So he coined the term the triple bottom line, which was originally for business, but has been adopted for sustainable practices as well. So this includes three different components. The first is the supporting of economic growth. So in our case, making pavements cost-efficient, fuel-efficient, energy-efficient, and so on. Also reducing environmental impacts. So that's the reduction of emissions, of pollution, of resource use, and so on. And finally, we also want to meet societal needs. So for the transportation infrastructure, that means having a safe infrastructure for people to drive on that's secure and also satisfying or comfortable for the user. So there are a couple of different ways that people have approached evaluating sustainability, since, as you can see before, it's a pretty comprehensive topic with these three main elements. So the first is to use a sustainable rating system. So this is more or less a qualitative approach where you generally have a checklist of different kind of components, and you go through and see if the project meets each of these criteria. They get a rating based on that. An example that many people are familiar with is the LEED system for buildings. So it's a sustainability rating system. On the federal highway administration has recently come up with INVEST, which is an voluntary tool that states and agencies can use to evaluate a project or to do system planning or operations and maintenance. So that's been used pretty widely over the US in the last 2 or 3 years. The second is carbon footprinting, which is also a fairly popular method for many different disciplines, but that's more quantitative, so looking at the carbon emissions, carbon dioxide mostly, and greenhouse gases that are emitted from a system. And then finally, we have a life cycle analysis approach, and which we'll talk about more in detail, but it considers the life cycle of the system. So from the production of the materials that go into the system, and then finally the disposal of the system. And in this case, a lot of agencies currently use life cycle cost analysis. And today we'll be talking about life cycle assessment, which is the environmental kind of life cycle approach. So simply, this can be defined as a method to assess the cradle to grave interactions between the environment and the product system. So for any general system, we typically have 4 stages. You can see the material production, assembly or construction of the system, the use of the product system, and finally the disposal or recycling of the system. And you can see here that with life cycle assessment, we would go through each of the stages and we look at all of the processes that are involved in the stage. We look at all of the inputs, the energy and fuel usage, as well as raw materials. And then we look at the outputs, for example, to emissions, to air, water, and soil. So why use LCA? There are a couple different reasons for using LCA. The first is that it is a quantitative approach as opposed to, for example, the sustainable rating system. So you can actually quantify environmental emissions such as greenhouse gases, fossil fuel depletion, ecotoxicity, eutrophication, and so on. Next, you can evaluate improvements in sustainability goals using concrete numbers. And third, since we are, as you saw before, going through the entire life cycle of the system and looking at each of the processes pretty intensely, you can pinpoint where the largest contributions to environmental impacts are and be able to determine where investment might be most effective. And just a illustration of where life cycle assessment fits into the sustainability ideology. So we have sustainable rating system as more of a social measurement, life cycle cost analysis for economics, and then finally life cycle assessment for the environment. So now we'll move on to an overview of the overall larger LCA study from which this work is taken from. So this project, the overall project is something that we've been working on for, I think, more than 3 years by now. So it's with the Illinois Tollway Authority up in Chicago, and you can see their network here. So the idea was to develop a complete roadside LCA tool for the agency. And by that we mean not just the pavements, but the roadside components such as drainage, structures, lighting elements, landscaping, and so on. So to be able to combine all 5 of these modules, we call them, into one single tool and be able to evaluate a more comprehensive system. So life cycle assessment is a set methodology that has guidelines and they've been set forth by ISO, which is the International Standard for Organization 14040 series. So they recommend a set of terms to use and a set of methodology and steps to perform LCA. So in general, there are 4 different steps. The first is the goal and scope definition, which is to define the intended audience, the intended application, the rules that you're using to perform the LCA, the system boundaries, allocation, and different definitions. And the second is the inventory analysis. So that includes all of the environmental data, essentially, so how you're doing data collection to get the emissions and the fuel usage that you need to perform the study, and how to validate the data and how to assess the data quality. And then after that, we have the impact assessment. So we have the emissions, but we need to translate them or characterize them into actual environmental impacts. So these would be the global warming potential and maybe human carcinogens and so on. And then finally, we have the interpretation. And as you can see, it's kind of a interrelated process because LCA is a very organic procedure that requires a lot of going back to, after you collect your data, seeing if it fits the scope and whether or not you need to change the scope and so on. So it's kind of an iterative process. Okay, so I'll go through just highlight each of the different steps that we just talked about. So the system boundaries, this is for the overall project, includes the 5 different LCA stages that are typically used for pavements. So we have materials, construction, maintenance, and rehabilitation, use, and end of life. And as we mentioned before, the inputs, energy, also electricity inputs, and different resources. And then we also have the outputs to emissions, to air, to water, to soil. And for each of these stages, we have, for example, in the materials, that's the production and acquisition of the raw materials, as well as the transportation to site or to a plant. And we also have mixed production, so at the concrete or asphalt plants. For construction, we have transportation of the materials to the site, equipment usage, the fuel burned and consumed during the actual construction activities, the placement of the materials, and also traffic delay caused by the construction. For maintenance, we have minor repairs and also major rehabilitations included. For the use phase, this is typically the most complex. We have to consider pavement deterioration and different models to look at that, rolling resistance, albedo, and carbonation for concrete pavements. And finally, end of life, we have to see what happens to the pavement system at the end of its design life. So that would be the transportation off or on-site, landfilling, recycling, reuse, and so on. So the different pavement types that we've considered in the LCA tool, it can look at flexible pavements, rigid pavements, as well as composite pavements, and these represent the types of pavements that are used by the Illinois Tollway. We are not looking just at mainline, but also at the shoulders and the ramps. And we can include kind of supplementary items such as pavement markings and traffic barriers, delineators, signposts, mileposts, and guardrails as well. So moving on now to the inventory analysis, so the second step. Since we are performing the study specifically for an agency which has a very specific context in the Chicago area, we need to use data that is regionally and temporally representative of the agency's context. So our preference was to get local surveys and questionnaires. We've worked with a consultant group to do this, but we supplemented with other data sources as necessary. As you can see, we looked into commercial inventory databases. A lot of these sources are based in Europe, but we didn't really have a choice in that case. We also looked at that literature and government reports, and we use different softwares to simulate emissions from construction equipment as well as on-road, off-road vehicles. So after we collected all of the inventory data, we used a commercial life cycle assessment software called CIMA Pro, and we're able to create models to kind of trace the process of each of those stages that we looked at before. And then we also needed to validate our data and do benchmarking to literature sources and so on to make sure that our models were correct. So an example of kind of the modeling process and the extent to which we looked at, considered the system, I'll just give an example of, for example, the process that we went through with the hot mix asphalt plant. So we considered, for example, raw materials and transportation to the site, as well as fuel production and transportation to the plant, and electricity generation and transmission, and that electricity was specifically for Illinois because many different regions have very different grid mixes depending on where they are. And then we also have the direct greenhouse gas emissions and other emissions that come from the asphalt plant. So for each of these processes, we trace back, for example, for binder, which we'll talk about in a bit, we have to trace back the production, all of the steps, and look at what we call the upstream emissions. So not just the downstream emissions here from the final process, but also everything that goes into it, how the electricity is generated, how the fuel is extracted and processed and transported, and so on. So we'll kind of zoom in to this particular raw materials, asphalt binder, to go into a little bit more depth about how the modeling process is done. So when we were, as you can imagine, there are a lot of different processes that go into an LC, so we had to decide which ones would be best to focus on and to really try to model with as regionally correct data as we could. So one of the major items that we picked was asphalt binder. And even though it consists of only about 5 to 7% by weight of a mix, it has the highest environmental impact out of the materials used in asphalt mixtures typically. So you can see here we have different percentages of binder and the energy consumption from producing the materials in these mixes. And you can see the other mixes in the orange, very small percentage is the transportation as well. In the binder, you can see goes from 40% to 91% of the environmental impacts from all of the materials that go into the mix. So it made a lot of sense for us to look at this process more carefully. So with asphalt binder, if you go back to its production, you have to look at crude oil extraction because it is an oil product. So crude extraction and flarings, and this is something that we paid particular attention to because depending on where the crude is extracted, the environmental impacts are different. And especially, for example, you can see flaring, depending on the country that the crude oil is coming from, the flaring is very different. For example, in Nigeria, they have a very high flaring rate, mostly because they don't have the infrastructure to capture the gas to put it into natural gas market. And then we also looked at crude oil transportation, which is also very influential. You can see we're in this PAD District 2, the Petroleum Administration for Defense District number 2. That's the Midwest District in the US. And the crude oil that we use in the Midwest, about almost 60% of it is domestic, but 40% approximately comes from Canada, and about 6% total come from different countries out of the US. So we'll need to consider the transportation that is required to get the crude oil to the refineries in the Midwest. So these were a lot of the different details that we had to consider as we were going through the life cycle analysis for the production of asphalt binder. And then just moving on, after the crude oil is in the refinery, it has to get refined, and we were able to look at the different refineries consumed, or the different fuels consumed in the refineries in the Midwest region. So you can see an example of the mix there. And then another interesting thing that we looked at, so these are different regions in the US. Again, we're the second one. You can see in the refinery, they're pretty different across regions and individually as well. But the production of asphalts out of the entire pool of petroleum products does vary from less than 2% to almost 8% in the regions in the US. So all of these variabilities we tried to take into account as much as we could as we were modeling this production of asphalt binder. So moving on to data quality assessment. So this is also a step in inventory analysis. We picked 5 different types of assessment to look at. So the first was time period. So this is ensuring that the data that we are looking at, are considering, is within a reasonable time period. It's not outdated. So our data was collected from 2012 from surveys that were distributed in northern Illinois. And we also looked at geography, for example. So since we were eventually going to model processes in Illinois, it made sense that we tried to get our data as close to this region as possible with the different models that we were creating. For example, for asphalt binder, again, looking at that Midwest region, electricity, we used the mix that is used in Illinois. We also looked at hauling trucks with a simulator of the emissions that are present in Illinois. Also technology, making sure that we consider relevant technology to the tollway, such as warm mix technology, as well as looking at recent IDOT and tollway standards to make sure that the models that we were processing, or that we were modeling, were correct. Representativeness, so we were looking at actual designs and mixes and standards from the tollway again, and also had collected data from tollway contractors and plants, so we're trying to get a very representative set of data. And finally, completeness, so making sure that we capture a good % of the processes that are included. And in terms of this, many existing studies out there do not include things like markings and signs included in the roadway. So that's something that we tried to complete to make sure that we had a better completeness in the study. So the third step in the life cycle study is impact assessment. So that's, again, translating those emission values, CO2, sulfur dioxide, and so on, into actual environmental impacts. So this was done using the U.S. Environmental Protection Agency's Tracy method, so that was developed for North America specifically. And we also looked at cumulative energy demand. So the 4 different types of impacts we studied were single scores. So this is from that Tracy methodology. And it looks at about 10 different impacts and weights them and normalizes them into a single indicator score. We also look at global warming potential because that is a very well-known impact right now. We look at total primary energy as well as primary energy as fuel. And the difference between that is that the total primary energy includes what's often known as feedstock energy, for example, from plastic material and asphalt binder, for example, because that includes oil and fuel products, but is not actually used as a fuel, so it has embodied energy within it. So now I'll move on to the development of the LCA tool and kind of give a brief description of how the tool was developed and kind of the major considerations and design processes behind it. So as I mentioned before, we have 5 different modules in this tool that you can see here in the picture again. And each of the modules considers the full life cycle where applicable. So you can see we've combined the materials and construction together. We have maintenance, use, end of life. Where applicable just means that a couple of these phases, for example, the landscape module does not include the use phase, but it includes all of the other phases. So we decided to use pay items as a basis for our tool because it is used widely by contractors and agencies at this point. So it would facilitate the implementation of LCA into the existing framework that agencies use right now. So for the pay items, we defined it using these 4 different categories, or 4 different components. The general characteristics of the pay item, the materials used in the pay items, the equipment, and then the design, mixed designs if applicable. So we'll get into that a little bit more because that kind of forms the basis of the tool. So cutoff criteria. So the number of pay items in a project varies very widely depending on the size and the type of project. It can be a couple hundred to, almost like maybe 500 pay items. So it ranges quite widely. And obviously we can't look at all of these pay items because as you can tell with the process of LCA, it takes a long time to get all of the environmental data to model things. So we came up with a cutoff criteria with our consultants to have a manageable number to do the analysis with. So there are 2 criteria for this. The first, it's based on the cost of the pay items. So first we order the pay items, as you can see here, from most expensive to least expensive. And we include the top 95% of the total cost. And then after that, we also make sure that we include all pay items that contributes greater than 0.5% of the total cost. So usually that fits within the top 95%, but occasionally we have to consider a couple more beyond that. So just an example of an actual list of pay items you can see here. We have kind of the cumulative percentage, and it goes down to 95 here, and in this case it's the same. So we have the individual pay item contribution. So the first one, for example, is 40%. It's a concrete pavement item. And then we go down to 0.5%, and it happens to be the same in this case, but occasionally it is not. So an example of that defining of the PATM, the diagram that I showed earlier, how it's actually done in the tool. So we have the general characteristics. So that's the description and the ID, but also the units, the productivity. For example, this is a fly ash compensated Portland cement concrete pavement, 12 inches. So the productivity, square yards per hour, the cost, material wasted, any notes. So we need these general characteristics when we're defining the PATM. We then look at the materials. So for this particular item, we have tie bars and bar support and so on. And we have the quantity. And then we also need to specify the transportation distance from the source to the site, because that is very important. Next, we have the equipment that's used for the PATM. So for this particular PATM, we have a concrete paver, a work bridge, a concrete saw, and so on. So we specify the HP, the fuel usage, the technology, and then if it's not being used, the idle time and mobilization distance to the site. And then finally, if there are mix designs, for example, this PATM is a concrete pavement, so it does have a mix design, then we actually input the mix design in. You can see the materials again, the amounts, and the transportation hauling from the quarries or wherever the cement plant is to the plant itself. Okay. So the overall tool framework was built in such a way to ensure that there was consistency among all of those 5 modules. So it's built with in a series of Excel files, and we have first the master workbook, which has a couple of different functions. So it can actually perform an LCA. So for example here, and we have something we call a generic LCA workbook, because as I mentioned earlier, all of the modules go through those same life cycle phases: the material and construction, maintenance, use, end of life. So we have a framework for that, a template, which I could say workbook. And then we use Excel add-in files, which basically supplement Excel workbook files, to provide any module-specific items to the generic workbook. For example, if there are specific maintenance schedules from lighting, from structures, from pavements, they're all included in these add-in files. And then within the generic workbook, we have the database of all the environmental impacts and the database of all the PATMs used. So this allows us to maintain a very consistent look and process to each of the different LCA modules when the user uses it. And then finally, we can also produce reports with this master workbook. So now I would just kind of walk through a little bit more of the LCA tool with some screenshots. So yeah, as I said before, it's implemented in a series of Excel files with extensive use of Visual Basic for applications and graphical user interfaces. So this is the navigation page, and you can see each, again, of those different stages: the materials construction, maintenance, rehabilitation, use, end of life, and so on. That is common to each of those modules. And then the different LCA stages, we have materials and construction. So as you can see here, it's based on PATMs. So the user will pick all of the PATMs that are needed in the initial construction phase, and they can go through that definition of PATMs that we just walked through before to ensure that they're as customized as possible to the project. And then we have the maintenance phase. So we can define a list of activities based on year for the pavement's life cycle. And then for each of these activities, we have different tasks. So for example, in year 11, there's some minor repairs that happen. And within those minor repairs, we define them as sealing the joints, microsurfacing, and so on. And again, since we're basing everything on PATMs, each of these tasks has its own PATMs that constitute the task. And then we have the use phase. This is an example of the pavements use phase. And you can see it has rolling resistance, albedo, carbonation, and that will be different for each of the modules. And then finally, we have the end of life. So we based on all the materials that are used in the PATMs, from the materials and construction and maintenance, we look at the different categories. For example, for pavements, it's asphalt, concrete, and aggregate. We can define what % of the asphalt is landfilled, what % is recycled, and what % is reused, and so on. So eventually, after we go through the entire LCA process, then we sum the impacts over the pay items, because that is, again, our basis for the calculations. So just to walk through this quickly, we have the total environmental impacts of the project, and that, again, is summed over all of the pay items, so that's represented as P here, over the set of the pay items. And then we have the quantity of each pay item. We have the percent waste of the pay item that's defined. And then we have the environmental impacts from acquiring and producing the material. We have the environmental impacts from transporting the material to the site. And then we have environmental impacts from the use of the equipment itself, environmental impacts from the transportation or mobilization of the equipment, and then environmental impacts from other processes, such as mixing in the plant. And then finally, outside of that is the use impacts from, for example, vehicles driving on the pavement are changing the lights, the light bulbs in the lighting module. So the second part of the presentation is going through the sustainability strategies that have been analyzed with the tool. So this is an application of the LCA tool that we've performed recently, and we are assessing environmental and economic impacts of different mix designs and pay items used in pavement construction. And the reason that we chose mix designs and pay items is because they're already in a framework that we can take directly from the agency, for example, because they include a list of pay items in all of the projects that are bidded out and so on. So it's very accessible for us to use. So for the mix designs, we had approximately 500 each, or 450, 460 of asphalt concrete and Portland cement concrete mixes. And these were used by the tollway from 1998 to 2014. And then we looked at pay items that were from pavement-related projects, 9 major projects from 2005 to 2016 by the tollway. And the environmental impacts that I'll be presenting are specifically greenhouse gases and energy consumption. So we defined the system boundaries of these 2 mixes and the pay items as cradle to gate, meaning the cradle from raw material production to transportation, plant operations, but then it ends at the gate of the plant. So that's where we stop counting the impacts. We don't consider transportation to site or anything after that. For the pay items, we considered cradle to placement, meaning we consider everything here for mixes, but also if there are other materials that are needed, we consider the production of those as well as transportation. We also consider on-site equipment usage, but we stop there at the placement of the material into the roadway. We do not consider the use or maintenance. So first, I guess looking at the mixes, these are the asphalt concrete surface mixes. They don't contain any recycled material because we wanted to show kind of the differences between the types of mixes that we're looking at. These are surface mixes. And you can see a breakdown of the contributions of different processes. For example, the blue here is the binder production, and then we have aggregate production in orange, transportation in yellow, and then plant operations in green. And as you can see, the 2 major contributors are the plant operations and the production of the binder. So something that was interesting is if you look at the transportation contributions at the end, they're quite a bit higher because these are high quality mixes. They're SMA and open graded friction courses. And we don't have very high quality aggregates in Illinois, so the tollway was having to truck them in from Wisconsin. So that's a lot of the transportation impacts there. And then we have here the recycled asphalt concrete surface mixes. And on the left we have energy, and on the right we have greenhouse gases. So you can see, as expected, as you increase the recycled binder content, the environmental impacts are decreasing. But you can also see that the transportation does provide some variability, and it's possible that transportation and also some modified binders here it's actually lessening some of the environmental savings that we have, as you can see kind of in this irregular pattern. So moving on to the Portland cement concrete mixes, These are mixes, are different types of mixes here. We have for pavement, we have for pavement patching, for pre-stress, precast, and also for precast concrete. And as you can see here, there is a differentiation between the different types of mixes, mostly because of the cement content. So for example, for the pavements, there's typically, I think on average in the sample that we had, about 500 pounds per cubic yard of cement. But for the other ones, they're closer to 600. And as you can see, the cement definitely is the highest contributor to the greenhouse gases, as expected because of calcination. But then there's also some transportation costs that are quite high as well. And then you can see the effect of different supplementary cementitious materials. So in this case, it was fly ash and also blast furnace slag cement. And there is a general decrease, but it also varies across the board. So next we'll move on to looking at the cost in addition to the environmental impacts together. So here we have the asphalt concrete mixes, and we have the cost on the bottom here, dollars per cubic yard, and we have the energy. And something interesting that we noticed was that there was kind of a little separated area there, and that that reflects actually the modified binders. So what this tells us is if we expect energy and cost to be pretty linear in relationship, because energy is often a factor of the fuel, which costs money. But if something is kind of away from that pattern, it tells us that, for example, here, the energy is relatively higher than the cost. So it's also the same way here with the Portland cement concrete mixes. But in this case, we can see a stratification of the type of concrete mixes. And it's again because of the cement percentages that are in these mixes. Pavement concrete mixes had the lowest amount of cement, and then the highest with the precast and so on, and the patching especially up there. So that tells us that maybe the cost and the energy impacts are not exactly related to each other, the environmental impacts are higher than the cost. So that's something that perhaps could be considered in policy or different decisions. So something similar we see here for greenhouse gases, especially for the Portland cement mixes, but it's less so for the greenhouse gases. Typically, the energy consumption for asphalt mixes is higher relatively than its greenhouse gas emissions because of the type of fuel that's used in the production. For example, coal has a much higher greenhouse gas emissions than natural gas for the same amount of energy. So now we'll move on to the pay items and looking at the contribution of energy from the pay items itself. So here I have from the left paved shoulder removal, granular embankment, pavement removal. And then on the right, we have kind of upper layers, so sub-base shoulders and also full depth hot mix asphalt. And we'll kind of go through these in stages. So here we have material production, and you can see the variation. For example, there's no material production for removal processes. And then we have material transportation, so a lot of that is going off-site, for example. We have plant operations, which is only needed for the right side here. You can see the contribution of that. We have plant-to-site transportation. And then finally, we have equipment usage. So we can see that depending on the type of pay item, that the processes that are contributing to the energy are different. And that's something that can be useful to help us pinpoint what are the major contributing factors to the energy. And this is just the total. So before we had percent contribution, so this is the total energy per square yard for these processes. And as expected, again, we have the higher percentages or higher energy impacts from pay items that have a lot of material, like full depth asphalt and shoulders. Okay, so moving on to the cost for the pay items now. So this is based on a actual full depth project from the tollway, and it's using the actual quantities. So we looked at the pay items that are included in the top 80% of the cost. So here we have the relative environmental impacts of the energy and greenhouse gases. And then on the bottom, we have the relative cost contribution. So if the items are in this area, then it has a relatively higher environmental impact than its relative cost contribution, because we are normalizing them. And then on the bottom, we have items that fall into this region will have a higher economic impact rather than environmental impact. So if we look at the highest contributing items, they're the full depth asphalt, 15 inches, and there's some places where it had 12 inches, but not as much, which is lower. The shoulders, and then also a bridge approach slab. We can see that most of these have a relatively higher environmental impact than their economic impact. And then we move on to subgrade aggregates, our capping material, and then embankment. And these are slightly lower and or have a slightly relatively higher economic impact. And then also removal processes, excavation, and so on also have a slightly higher economic impact as opposed to their environmental contribution to the project. And this is just everything in order. So I think this is about 12 pay items here. And then moving on to a project with concrete. This is, again, the top 80%. I think there are 10 pay items in this case. And we have the same regions set up. And looking at the pavement itself, it was 12 inches and 13 inches. And then the shoulders, warm mix shoulders, warm mix subbase, and then the transition slab. You can see here that the energy and greenhouse gas contributions are actually fairly different because of the very high amount of greenhouse gases that come from cement production. And so that's why the relative contribution of the concrete pavement pay items are higher than the energy. And then we look at the granular embankment and subgrade aggregate, and then finally the earth extraction and pavement removal pay items. And then we have everything together here. So the last thing that we did in our analysis was looking at a cost effectiveness value. So we wanted to see essentially what types of, how different types of sustainable strategies could be evaluated with both environmental and economic impacts looking at kind of the highest benefit for the lowest cost, basically for cost effectiveness. So the sustainable strategies that we looked at included different types of mix designs as well as technologies. And this wasn't for a particular project, which would be much better, but it was over the average of the data that we saw before. So this is a little bit of a busy slide, but these are the cost effectiveness values for the different sustainable strategies that we looked at here. So if we start at the top, the orange means that there is a cost that must be paid in order to get environmental savings. And the minus the blue values means that there's both a cost and an environmental savings. So that's definitely a win-win situation for these blue values. So on the left, we have the greenhouse gas cost effectiveness, and it's essentially dollars per kilogram of CO2 equivalents or greenhouse gases. And to give a baseline, we have in red here, it's the dollars per gallon, dollars per equivalent greenhouse gases from the combustion of a gallon of diesel. So that was in 2012 when this data was from, was about $3. So that's kind of what a lot of us who drive are willing to pay for the greenhouse gases that we are emitting from using 1 gallon of diesel. It's just $3. Okay. So I think this graph is, this line is actually supposed to be up there, but it's okay. This is correct actually, yeah, because it's gallons versus kilograms. So this is, I think that the value per kilogram would be something like 0.4 or something per kilogram, but it's $3 per gallon. So we can see here, these are the concrete, the JPCP 12-inch concrete sustainable strategies. So that's using 10 to 20% of fly ash or slag cement The second one is the two-lift concrete that the TOA uses quite a bit. And then the third, the transportation, is using 20% less transportation. And you can see that they all give a negative value, which means they both have a cost and environmental savings. For HMA surface mixes, again, we have different values of recycled material, and as they increase, the cost effectiveness gets even better. Except for this warm mix, I think it's mostly the cost, right, is a little higher for warm mix on average from the data that we evaluated, which is why it's giving a positive value. So in that case, there may be a cost that has to be paid in order to get those environmental savings. And then finally, we have also SMA mixes, where we have increasing amounts of recycled material. We have warm mix, which tends to include a lot of recycled material, so that's why it has this negative cost effectiveness value. And then finally, transportation. So you can see in general that transportation typically has the highest cost effectiveness, which is good for us. Mostly because if you're decreasing the transportation, you're just getting rid of the environmental impacts from that transportation. Whereas for things like recycled material, you're getting rid of the environmental impacts from producing virgin material, but you still have to pay for the processing of the recycled material. Okay, so a couple final remarks to finish up. So LCA, as we've seen, is a holistic and systematic method of evaluating the sustainability of pavements. And it's important when you're developing a tool to, for us, to develop something that is implementation focused. So for example, the use of pay items so that it can actually be adapted by agencies in a more reasonable and practical manner for them to do. We also looked at mix designs and saw that the hauling distances and also modified binders that are used can lessen environmental benefits from using sustainable materials and technologies. And finally, when we looked at the cost and environmental impacts, we saw that there is definitely a correlation with the cost and environmental impacts, but sometimes by looking at how they may vary from that equality line, we can see that there is a relatively higher environmental versus economic impact, or a relatively higher cost versus environmental impact, which kind of makes us think about how we pay for our emissions, basically, that we're using. And then finally, we looked at some common sustainable strategies, and we saw with analysis that many of those strategies have both economic and environmental impacts, which happens in the correct circumstances, again, depending on the differences in the specific context of the project. So I would like to acknowledge the Illinois Tollway Authority for the sponsorship of most of this project, and then the Illinois Center for Transportation, as well as our consultants at Applied Research Associates and the Right Environment, and also many of the numerous other professors that were involved in this work and graduate students that have been involved in this project. So yep, that's all I have. Thank you very much.
We have really perfect timing at the same time. Floor is open for questions. Yes.
I'm just wondering if any of the final remarks or the conclusions would change differently with the change in the gas prices. I mean, I assume it's just a parameter and it's
Sure.
The trend should be the same, but is there any scenario that you can see where maybe some of the conclusions will change?
Yeah, for example, the hauling distance, I mean, if it's getting even cheaper and cheaper to obtain diesel and to buy it, then people could see their cost-effective value differently. They could be willing to spend those environmental impacts because it's so cheap to do so.
It will affect the aggregate quality big time, and what's affordable for higher aggregate quality to go longer distances.
That's true. Yeah, people would be more willing perhaps to get their material from further away.
But wouldn't that imply that it's more greenhouse gas emissions? So how do you,
That's unintended consequences. That's cool.
Right,
But-
so
yeah.
I think, if I may go back really quick. Oops, let's see. So there's a kind of a, so I think these graphs here kind of maybe speak to that a little bit. So if, for example, the cost is much lower than the material, or with that lower, for example, transportation cost, the cost would go down, for example, over here, but the environmental impact would stay the same, maybe, or go higher. So you can see that it has a relatively higher environmental impact as opposed to the economic impact. And I think maybe in the U.S., like some of the policies right now are trying to bring those to equality so that you're paying the cost that is reconcilable to the environmental impacts. So I would see that the process for that with the higher hauling distance, but say like higher or the higher hauling distance and environmental impacts, but lower cost would push it into this range here, which may we'll see higher environmental impacts even with the low cost. Yes.
So better quality aggregates won't change the life of the pavement. Like for example, if you need to do some kind of rehabilitation, so if the quality of aggregates is better or material is better, then that like rehabilitation practices will reduce, and that might reduce the effect. So it will change the process or something.
Sure. Yeah, that's a good point. That the quality of the aggregates will also affect the pavement performance. So in this particular analysis, we didn't look at the performance of the pavements or the rehabilitation, but it was kind of a partial life cycle assessment. But with the full life cycle assessment, you would have to definitely look at the performance and the subsequent maintenance and rehabilitation as well. So that would.
So how will you decide? Like for example, same thing. If I decide to get better materials, let's say. So how will you decide like performance will increase this much?
Right.
Why?
I mean, it's hard to know what the performance. I think we were looking at some. We have to look at maybe historical data to see how the pavement life might change with higher quality aggregates. But for example, so here with the SMA and the open graded, it's expected that with the higher materials that these mixes will last longer or perform better. So even though they have this, it looks like they have a higher environmental impact, which they probably do because of the hauling and the quality of the materials and modified binders usually. But you would have to also consider that these are expected to last longer or have a different function than these other mixes. But that's not something we considered at this point. But definitely, good question.
Yeah, actually, in that context, when you think about it, like pavement management used to be the same way how you predict basically the condition of pavement going down, right? That deterioration, damage, basically, how damage is taking place in time throughout the life of a pavement. That's how we used to look at the LCA in that context in the old days, in the past. But now sustainability brings them all together in. But same missing item is still there, though, in my opinion, which is that deterioration mechanism for different payments, for different applications. We need to improve our understanding of how, again, just like, for example, better quality, how is that affecting the design life and the performance, which is all related to predicting that deterioration mechanism and the timing of that. I think that's always a challenging part for us to get that, bring that, the different types of payments and applications we're analyzing in the right picture.
Yes, definitely. I think.
This is the important part of the ME design.
The future of this kind of tools, I think, incorporation of this sustainability life cycle assessment or life cycle cost analysis tools within EPDG. So you consider those upfront in the design stage where you're picking really the materials.
Correct.
So when you do that, if you have a mechanistic tool in your hands, then you can also think about when you use a higher degree quality, if you're going to get maybe 2 years of additional lifetime in your payment, then you can incorporate that upfront at the very beginning, the design stage, whether paying maybe this much extra money would really benefit us in the long term. So
Sure. Well,
that will eventually be done.
yeah, my
somebody-
point goes back to
Yeah.
even some of the poor performance models that come with MEPDG or alike.
But better
So
MEPDG
how-
and then
how to-
with the better MEPDG in the future, whenever, yeah. Right now, it's even MEPDG cannot do that, even if you have a good quality aggregate, cannot predict extra lifetime. Any other questions? If not, I will just make a final remark for the two, for a praise for Rebecca. This, all the things that you have seen today was done with Excel. I mean, personally, I think that, I would never have imagined Excel really to develop a platform, such a tool like this CA tool. So, and I was always thinking that if we can send this to Microsoft Excel to see their actually boundaries, what they can do with Excel. I mean, this is really such a nice, sleek tool, and then it's all developed in Excel, Microsoft Excel. And thanks for attending the presentation. I guess I'll see you next week for another Kent seminar.
Thank you.